Swayam Prabha. Digital India. Educated India.
Hello and welcome back to another lecture of this course on robust control. In this lecture, as in a few past lectures, we shall again be revisiting, for some of you revisiting and for many of you probably refreshing or maybe introducing concepts from linear algebra, which would then potentially aid us in many of the analysis, much of the analysis that we carry out in this course thereafter. So, in the previous lecture what we introduced was the result of this so called Rank-Nullity Theorem for linear maps between two vector spaces, right. And although I did not prove it, I gave you a very loose interpretation of what this rank nullity essentially implies. I realize that I use this term that one vector space is richer now and than the other, yeah. So, when I said, like, for example, if you have a one-on-one mapping, a one-to-one mapping, that is an injection, that is if A depicts an injection, then you have the fact that the kernel of A is just trivial subspace, the trivial subspace, and therefore its dimension is 0, right. In that case, it turns out that the image of A has exactly the same dimension as the dimension of V, right. Now, V, remember, is the domain, and image of A is basically a subspace of the codomain. So, this might lead you to conjecture that, well, the dimension of the codomain is at least as much as that of the domain, and therefore, I loosely said that, then the codomain is richer than the domain. By that, I do not necessarily mean, and I want to clarify that the codomain contains more points than the domain, because you remember, you see, when we are trying to count the number of points in a set and compare it with the number of points in another, or number of elements in a set and compare it with the number of elements in another, the way to go about it is, if we can find a bijection, and here is the crucial bit, not necessarily linear. As long as we can find a bijection between two sets, we say that their cardinalities are one and the same, alright. And it turns out, funnily enough, that even though it is not a linear bijection, but there do exist bijections which allow you to prove that, well, R and R2, that is the real line, and the plane R2, yeah, they contain exactly the same number of points. Very counterintuitive, but such funny things do exist and such funny results do exist, right. So, when I say richer, I mean it in the context of a linear map. Do not go about thinking that, well, one subspace contains more points or more vectors than the other. Okay, that would be an incorrect interpretation of what I said. So, I wanted to just put that out across before we get too far with this. Right. So, the first thing we are going to try and do is see a rough sketch of the proof of this result that you see on the screen right now, called the Rank-Nullity Theorem. Okay. Okay. So, here is what we do for a proof. Again, I will probably not write every single step in great detail. So, remember that the kernel of A is a subspace of W, and therefore has a basis. Of course, we are assuming that these are all finite dimensional vector spaces. This W is a finite dimensional vector space. So, therefore, any subspace of W, these all, by the way, require some small technicalities which I am sort of pushing through without getting into too much rigor, but it stands to reason that a subspace has a dimension which is at most equal to the parent space, right. because after all the definition of a subspace is that it contains every element in that subspace is at least contained in the parent space, right. So therefore, we assume that if W has a basis, a finite basis, that is the cardinality of the basis set is finite, then so is the cardinality of any basis of a subspace of W, and clearly kernel of A is one such subspace of W, and therefore it has a finite basis, say of cardinality K, alright. So let us just assume that this basis for this kernel of A is given by, what should I call these vectors, okay, let us say P1, P2 dot 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 till Pk. And here is the interesting result, again something that I am not really going to sort of prove, it is just like an axiom, you can treat it now for the time being, the fact that if I give you a collection of linearly independent vectors in a vector space, you can always extend it to form a basis for the vector space. Why is that important? Because remember, the moment I say that this particular set is a basis for the subspace that is kernel of A, this turns out to be a linearly independent set in W, right. So this set is contained in kernel of A, which is in turn contained in W, right. So therefore, this basis that I have just put it to you as a basis for the kernel of A is a linearly independent set in W as well. And as I just said, any linearly independent set in a vector space can be extended till it forms a basis for the vector space, right, because remember how we described it, it is a maximal linearly independent set, okay, a basis is a maximal linearly independent set. So at that stage you will call it a basis when you cannot add any more vector to the set without violating the linear independence of that set, right. So what you can then do is, given a linearly independent set, so given a linearly independent set, so here is the trial, maybe an example. So consider span of this P1, P2, so on till Pk. Now this is obviously a subspace, right, we have already seen that this is a subspace, isn't it. Once we know that this is a subspace, now you check. So this is like a constructive way of checking, check to see if there is any vector P such that P belongs to W, but P does not belong to this span of P1, P2 dot 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 till Pk. Okay. In other words, P belongs to, in set theoretic notation, we write it as P belongs to, so this is not necessarily a subspace, it is a subset, okay. Take the set of all vectors that are contained in the subspace W, yeah, and take away all those, so this is set minus, this is subtraction of two sets, and take away all those vectors which belong to span of P1, P2 till Pk. Yeah. So if there exists such a P, then what you do is you append this P to this erstwhile set, that is P1 through Pk. So now this set begins to have k plus 1 elements, and it is guaranteed that this set is, this new set that you have cooked up by appending this is going to be linearly independent. Why? Because if it were not linearly independent, then P could be represented as a linear combination of the vectors P1 through Pk, and therefore it would belong to the span, thereby violating the fact that it does not belong to the span. So this is a sure shot method of cooking up or extending the linearly independent set in a vector space till you get to its basis. Okay, you can carry on, then you get k plus 1 elements, then you consider the span of P1 through Pk and P, k plus 1 elements, and try to find out if there is any other vector in W which belongs to W but does not belong to the span of these k plus 1 vectors. If it is still possible to get such a P, include that. Then you got K plus 2 elements, right? You keep extending like this until you are unable to find. So, I realize this is in a very abstract notation, but not very constructive, okay. How to search for this element, how do we go about this efficiently. So, I am not getting into this programming business or this coding business, okay. I am just giving you the abstract idea of why for a finite dimensional vector space, given a set of linearly independent vectors in that vector space, you should always be able to extend it and you will always reach a stopping criteria whereupon you would have arrived at the basis for the vector space, right. Why is this very crucial? Because now we are going to use exactly this result, okay. So, let me put this in a red box and return to the Rank-Nullity Theorem, okay. What does the Rank-Nullity Theorem say? So, now we have assured ourselves that there does exist a basis for the kernel of A, where each element from this basis also belongs to W, because after all the kernel of A is the subspace of W, alright. Good. Now, because of this discussion that I have just had, you should be immediately able to see that extend, when I am saying this in a one sentence, I am saying this like in one fell swoop, I am claiming it can be done, but I have given you enough justification as to why it can be done. Now, extend B kernel A, which is the basis for the kernel of A, this set, to BW, where BW is a basis for W. Why can it be done? Because look, this set is after all a linearly independent set in W, as I have just shown you here, and any linearly independent set in a vector space can be extended to be a basis for the vector space itself. So, this can be done, this is doable. So, suppose okay, I have to recall what I have chosen the sizes of those, have I said what the dimensions are? If I haven't, oh well, yeah, I can choose it to be M. Suppose dimension of W is equal to M. So, clearly then K that I had chosen earlier, this dimension of this kernel of A, it is less than or equal to M because it is a subspace of W. So, therefore, let BW, what will it look like? Of course, the first few elements will be exactly the elements that you inherited from the basis for the kernel, and then you extend it W1, W2, how many? In all you must have M elements, so then you go on till M minus K, right, count, there are exactly M elements in this set and this is a basis, such a basis for W, alright, fair enough, we are all clear up until this point, I hope. Now, once we have got this, so this is not really, yeah, it's a very bad mistake, I am terribly sorry about this, yeah, it's just that I reversed the entire whole thing here, right. So, this is going to be basically V. So, what I am saying is that let us extend this, everything that I have mentioned here will now be reversed, I am very sorry about this should be actually V, yeah. So, I was constantly talking about the codomain, sorry about that confusion, it is a really bad mistake, it is only later that I noticed this, okay. Okay, so what we have is this V here. Okay, so then obviously the extension of the basis still holds. Everywhere I have written W here. Remember, kernel is not a, it's bad. I was somehow in my mind I was processing it in the opposite sense. So let us make this N, all right. Let us make this N to be consistent here. Yeah. Okay. Yeah. And let us call these V's, why W's? W does not make sense, right. This is V1, V2, so not much damage done. except for maybe to confuse you slightly, but yeah, I hope that this will not really be an impediment. Okay. What I am saying is, look, I was earlier mistakenly saying that this kernel is basically a subspace of W, but since it is a mapping from V, so kernel is obviously a subspace of the domain, not the codomain, right. You can clearly see that the way we have defined the kernel here. Let me go back to the previous day's lecture where we defined this kernel. Yeah, see, kernel is basically a, so I have already mentioned this in the previous lecture, kernel is basically a subspace of the domain V, right. So therefore, to catch a breath and to sort of reaffirm this, so the kernel has a basis P1 through Pk, yeah, and therefore it is also a linearly independent set in V. Because it is a linearly independent set in V, it can be therefore extended till we obtain a basis. Much of the notions still hold, except the fact that I messed up with this V and W, because the kernel is basically a subspace of V of the domain, not of W. Yeah, the image is a subspace of the codomain, that is W, right. But the idea of extending a linearly independent set in a vector space to be a basis for the vector space itself still carries. It is independent of this domain, codomain, whatever we have defined. It is a fundamental idea. The point is that for the kernel you have a basis of size k, cardinality k, right, and then you extend that set of vectors of containing k vectors which form a basis for the kernel till you get a basis for V. So you have to only add n minus k new vectors to it, right. So then this V that we pick from the domain can be written as alpha 1 P1 plus alpha 2 P2 plus dot 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 till alpha k Pk plus beta 1 V1 plus beta 2 V2 plus dot 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 till beta n minus k Vn minus k, right. So now when you act on this vector V using the linear map, when you hit it with the linear map, now AV then turns out to be alpha 1, again due to the linearity of the map, alpha 1 AP1 plus alpha 2 AP2 plus dot 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 till alpha k APK plus beta 1 AV1 plus beta 2 AV2 plus dot 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 till beta n minus k A Vn minus k. Okay. All right. All right. Yeah. Okay. Yeah, we are good to go. Fine. So now, hang on, this is n minus k. Okay, we are good. Now what happens? Look at these elements. Yeah, look at these elements P1 through Pk. Where do they all come from? These all belong to the kernel of A. So if they belong to the kernel of A, then this basically gets mapped to the 0 element in W. This also gets mapped to the 0 element in W. So, right, likewise every element here gets mapped to the 0 element in W, right? That is the definition of the kernel. So basically then what you will be left with is beta 1 AV1 plus beta 2 AV2 plus dot 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 till beta n minus k AVn minus k. In other words, you take any arbitrary vector V in the vector space big V and you map it through this linear map A, and then this belongs to the span of, notice very carefully, what is this the span of? So this element belongs to W, this element belongs to W, all of these elements belong to W, right. So these, right, so this belongs to W. So any time you take an element in V and map it through this linear map A and take it to an element in W, then that element can be expressed as a linear combination of only n minus k elements at most, which is another way of saying that it belongs to the span of AV1, AV2 dot 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 till AVn minus k. Okay. So therefore, it turns out that the image of A, yeah, the image of A is contained in the span of AV1, AV2 till AVn minus k. Now remember, the span is a vector space. So how many vectors does this contain, the span? Yeah, it contains n minus k vectors. Now the dimension of this vector space will be exactly equal to n minus k when each and every one of these, yeah, is not redundant to this set. That is another way of saying that this set is linearly independent. And now we are going to precisely try and prove that, because if we would have proved that, then we would see that anytime you take an element in the vector space V and map it to an element in W using this linear map, yeah, you will need n minus k and exactly n minus k elements to represent it. Yeah, this holds true for any arbitrary vector. Okay, some special vector might not require all of them, but any arbitrary vector you pick in V, map it through this linear map A to an element in W, and then that will belong, yeah, to the span of these vectors, yeah. And moreover, the fact that these vectors constitute a linearly independent set tells you, yeah, that the image, yeah, is exactly equal to this span. Yeah. Another way of saying this is, if you want to prove two subspaces to be equal, yeah, you have to show that both are contained in each other. Yeah. So what we have seen here is that this, you take any element in the image of A, it's contained in the span of these vectors. Now on the other hand, if you can show that any time some element is contained in the span of these vectors that I have written here, it is also contained in the image of A, yeah, then we would be done, right. So what do we need to show in order to, what do we need to prove in order to show that? We need to prove that you cook up any vector in this vector space, you look up any vector in this vector space, right, and you try to see whether that vector belongs to the image of A. In other words, if for any linear combination of these fellows that you can think of, yeah, there does exist, yeah, some element in V such that V gets mapped to this, then we will be done, right. So can we do that? Unfortunately, the easier way out for me here would be to show that, well, this is a linearly independent set, okay, because if I can show you that this is indeed a linearly independent set, what would that imply? So I am just trying to show you the different ways in which these proofs can be tackled. I have already mentioned one way, I am not going to pursue that, but the method that I am going to pursue is that, look, this, any element in the image of A is contained, can be expressed as a linear combination of these n minus k fellows, okay. And now if I show you that these n minus k fellows are also linearly independent, then this set of vectors AV1, AV2, so on and so forth, this is not just a spanning set for the image of A, but this is also going to be a linearly independent set, yeah. So this is a minimal spanning set or a maximal linearly independent set. That is what after all a basis is, right. And on the other hand, if we can also combine both those properties for a particular set and show that this set of vectors is a spanning set for every element in this vector space, and this particular set is also linearly independent, yeah, the spanning part is already done. So if I can now show that this set is linearly independent, I will be done. So now suppose C1 AV1 plus C2 AV2 plus till Cn minus k Avn minus k is equal to 0. Now if I want to show that this is linearly independent, then I will have to show that the only way that this can hold, is when each and every one of these C's, these scalars, is equal to 0, okay. So let us see. So this means that A times C1 V1 plus C2 V2 plus till Cn minus k Vn minus k is equal to 0, right. So, therefore, it turns out that by definition itself then C1 V1 plus C2 V2 plus dot 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 till Cn minus k Vn minus k belongs to the kernel of A. Unless this fellow belongs to the kernel of A, I could not have hit this vector with A on the left, yeah, the linear map, and got a 0, right. Of course, this is a 0 in W. Later on we shall omit this, yeah, when it is understood from the context. Okay. But what does that mean? The moment I say that some fellow belongs to the kernel of A, then it can be written as a linear combination of the fellows in the basis for the kernel, because remember the kernel is also a subspace. So, anytime a fellow belongs to the kernel of A, it can be expressed as a linear combination of the fellows in A, in the kernel of A. But what is the basis for the kernel of A? That is exactly what I started my construction with, right. So, the kernel of A has a basis given by P1 through Pk, this particular set. So, therefore, there exists some D1 P1 plus D2 P2 plus dot 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 till dk Pk, right. So, therefore, this fellow, since it belongs to the kernel of A, must be equal to this fellow for some choice of D1 D2 so on till dk, right. But what does that mean? That means that C1 V1 plus C2 V2 plus dot 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 till Cn minus k Vn minus k plus minus D1 P1 plus minus D2 P2 plus dot 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 till minus dk Pk is equal to 0. I am bringing both on the same side. But what is this? Now you notice that the set V1 through Vn minus k and P1 through Pk, they also form a linearly independent set. Why? Because that is precisely the basis for the vector space V. And because of this fact, whenever we have this result, we must have, since this is a linearly independent set, we must then have C1 is equal to C2 is equal to C3 is equal to dot 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 till Cn minus k is equal to minus D1 is equal to minus D2 is equal to dot 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 till minus dk equal to 0. But I am not even interested in these D fellows, right. All that I am interested in is I have managed to prove to you that all these C's must vanish. Whenever I have a linear combination of these fellows to be equal to 0, I must also have all of these C's to be equal to 0, which means that the set AV1, AV2 dot 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 till AVn minus k is linearly independent, and I have shown you that this set also spans or generates, as you might prefer to call it, the image of A. Yeah, because I have taken you through this, I have shown you that you take any vector in V and let the linear map act on this vector V, and eventually what you get in W can be expressed as a linear combination of at most these n minus k fellows, right. You do not need any other vector. So, it definitely belongs to the span of this. So, this is a spanning set, it is a linearly independent set, and therefore, this is the basis. Therefore, AV1, AV2 dot 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 till AVn minus k is a basis for image of A, and therefore, the dimension of the image of A is going to be equal to the cardinality of this set, which is n minus k. But what is n? N is nothing but the dimension of V. What is k? Notice, by my choice itself, I have defined that the kernel of A has a dimension equal to k, that is embedded in this consideration, right. So, therefore, This leads to the conclusion that this is equal to dimension of kernel A, and ergo we have proved to you the rank nullity theorem for linear maps from one finite dimensional vector space to another. Yeah. Why is this very significant? It is particularly significant when you have a bijection, because when you have a bijection, then you will see that the kernel is the trivial subspace, therefore this dimension of the kernel is 0, and the dimension of the image is equal to the dimension of V, that is due to the injection part of the bijection, and due to surjection this image of A will be the entirety of W itself, right, because every element in W has a pre-image in V. So this image of A then reduces to W. So for bijection, image of A is equal to W, right, and kernel of A is equal to just the 0 subspace in V, right. So therefore what you are then led to conclude is that for a bijection you have dimension of W is equal to the dimension of V. This will be particularly important when we take linear operators, those are linear maps from a vector space to itself, because then W is equal to V. So trivially it is true that the dimension of W is equal to dimension of V. Of course the dimension of a vector space is equal to that of itself, goes without saying, right, the most fundamental starting point of anything, right, everything is equal to itself. Okay. So now what is the benefit of having such bijections, apart from the fact that, okay, from the rank nullity it gives us these elegant results? It also turns out that now suppose we have only surjection. Suppose we have only surjection, yeah. So suppose this is, much as I would hate to draw figures, I will have to draw some here to probably explain it better, yeah. So suppose you have a surjection, it means that every element here that you can pick out in this vector space W has a pre-image here, okay. It might be that multiple fellows, because it is not guaranteed to be 1 to 1, so it might be that multiple fellows map to the same element, yeah, but nonetheless there is at least some pre-image here, okay. So because of surjection you are assured that there is some pre-image, okay, great. So now what can we do with this surjection property alone? Now if you want to go from W to V back, yeah, there are two ways in which this can be accomplished. One, if you first pick out an element in V, hit it with the linear map A, and then potentially there is another A hat which is basically a mapping from W to V, yeah, which takes you back to V, okay. The other thing is, suppose you have a map already defined A tilde from W to V. So you take any element in W here, hit it with this map A tilde, and then again you hit it with this linear map that we have, and suppose this takes you back to the element W itself, right. Remember, both of these are then identity maps. Why? Because you hit any fellow with the linear map, yeah, A, and then you hit it back with A hat, right. So first time you are hitting it, you are taking it from V to W, and the next time you are hitting it, so as we keep piling up these operations, you keep seeing more operators pile up on the left, right. So first you hit it with A, go from a point in V, vector space V, to a point in vector space W, and then you hit it with A hat and you go back to that same point in vector space V. In the second case, what we are doing is, So, this is basically the equivalent of an identity map in the vector space V. On the other hand, in the second case, you are taking an element in W, you are hitting it with this map A tilde, which takes it to an element in V, and then you are saying that, well, now that I have gotten here, I want to now hit it with our known operator A, which is already known linear map, sorry, not operator, known linear map A, which now takes me back to W. So, this is then basically the identity mapping on the vector space W, alright, very important notion here. So, which of these is associated with injection, which of these is associated with surjection? That is the important question. I will not get into the rigorous theory, but I will try to give you some intuition and some insight into which of this works. Now, suppose the map is just a surjection, I am sorry, so let me mark it with a different, okay, let us just circle this. Suppose this map is a surjection, it means that under this mapping A, yeah, if you come through a mapping of A, of a linear map A from V to W, yeah, then already you can pick out any point out here without exception. You can pick out any point in this vector space W without exception, and it is guaranteed to have a pre-image in the domain that is V, right. How does this help us in constructing any of these two maps, let us say A hat or A tilde? How is it supposed to help us, right? So, take the first one for instance. I am just going to teach you give you an sort of an intuition, and it might sound like a shortcut. Now, think of it this way. Suppose you hit a vector V here and take it to AV here, and now you want to go back to this vector V, yeah. So, of course, if you have mapped it here, you will always be able to get back to this vector. That is not the point. The question to be asked is this unique? That is V the only fellow, yeah, is V the only fellow that has brought you here? Could it have been that there is some other V bar which would have also brought you here? Because if so, then you would be at a loss to define, right. So, think of it this way, you would be at a loss to define this. So, therefore, mere surjection does not help us here, right. On the other hand, if you had injection, yeah, if you had injection, if this map was an injective map, then once you have arrived at a point in the vector space W through this linear map A, you are sure that there is a unique path that has led you here. You will obviously, after you have arrived at this point in the vector space W, it is definitely the result of a mapping from V, right. So, there is a path to trace back. The question, meaningful question to be asked is the path unique? And it turns out that only if it is an injection, then this path is unique, right. So, therefore, we say that when you have a one-to-one map, then you have what is called a left inverse of the map. So, this A hat is a left inverse, okay. This will make more sense when you talk about matrices. I mean, if you have heard of things like pseudo inverses, yeah, or left inverses and things like that and so on and so forth, yeah. But I want you to just get an intuitive feel for why this must be so, right. Because think of it like a problem. You have arrived under a certain linear map to a point in W, and now you want to retrace your path back, but you find, well, under the same linear map there could be multiple fellows who would have brought me here. So, which path do I take now? So, you are at a loss to define the map. Only when you have injection property imposed, then this path gets uniquely fixed up, and therefore, you say that this is a reverse path. So, injection is absolutely essential to the existence of the left inverse, right. So, then it stands to reason that this must have something to do with surjection, as you might have guessed. How so? Now, think of it here, right. What is the first thing you are doing here? You are picking out a fellow here. You are picking out a fellow here, and then you are getting it to be acted upon by this map called A tilde. What if you have surjection? It means that every point here, every point in this vector space W has a pre-image in V. So let me do something. Let me just say whatever that pre-image is, let me just define this A tilde to be such that this A tilde will take me back to that pre-image, right? Okay. Now I am not really worried about not landing up here. Why? Because every map can at most be many to one or one to many. A map cannot be, sorry, many to one or one to one. A map cannot be one to many. Then it is not a map, no? You cannot have in the domain a single element mapping to two different values, right? Two different vectors in the codomain, right? That cannot happen. So think of it this way. I pick out a fellow W in the vector space W without any fear, because I know that the map is this A map is a surjection. So therefore there must exist at least one pre-image. There could be multiple pre-images in A, but no matter whichever pre-image I go to, I can define it to be any one of the pre-images. So when I define this A tilde, I can do this arbitrarily. If there are multiple pre-images, I take my pick, the one I prefer. I don't care which one. Okay, I just pick out any one of them and I say that, look, this A tilde will be such that I will pick out this and I will go there. Okay, once I have gone there, this fellow, this A tilde W is now an object in V, right? Because remember, the A tilde is a mapping from W to V. So now I have gone to V. Once I have gone to V, look, V could be a one to one or many to one. In either case, it is going to always land up in the same W. So suppose I define an A tilde in a certain manner. Suppose there are multiple fellows in V which map to a particular fellow in W. Suppose there are 3 fellows. So I choose one of those fellows for my reverse mapping A tilde. You choose the second fellow and another person chooses a third fellow. But whatever it is we choose, once we have landed up with this A tilde W, we will end up with 3 different fellows. I will choose this A tilde W corresponding to this W to be V1, you will choose this to be V2, and someone else might choose it to be V3. But then whether you hit V1, V2 or V3, once you hit it with A back again, you will uniquely land up in W. So you see that surjection indeed provides us a way of constructing the so called right inverse. Okay. So once you have injection, you can always get a left inverse for a map. Once you have surjection, you will get a right inverse for a map, and the same things by extension, because a map, linear map, is after all just a matrix represented in terms of some ordered basis. Therefore, you will immediately have these notions of left inverses of matrices, right inverses of matrices, and so on and so forth, right. So I would now invite you to take a sort of a exercise, not necessarily a written exercise, but a thought experiment of sort, or thought exercise, right. Think of it. Think of the sizes of the matrices, a matrix of size m cross n, right. So what is the dimension of the domain, what is the dimension of the codomain? Think of it in terms of rank nullity, yeah, and think of it as a full rank matrix, okay, full column rank or full row rank, yeah, and try to relate this. What does full column rank mean, yeah, what does full row rank mean, what sort of a matrix has full column rank? You will see a tall matrix has a full column rank, can have a full column rank, that is, if it is a full column rank matrix, it has to be at least a tall matrix, if not a square one. Similarly, a wide matrix is the only type of matrix that can have a full row rank, wide or a square matrix, right. Yeah. So relate those full column ranks and full row ranks with surjections and injections. Try to think of these, right. It is very important that you have very clear understanding of matrices, as we will see subsequently also when we delve further into these topics. We will see that these ideas are very, very pivotal, okay. So therefore, I have just explained this to you at the level of linear maps, and I hope that you have now some intuition about what surjection and injection lead to. Turns out if it is both a surjection and an injection, that is if it is a bijection, then you have both inverses existing and they are one and the same. Okay, at least insofar as a matrix is concerned, yeah, the left inverse of a matrix and the right inverse of a matrix, if they both exist, they have to be the same, and in that case the dimension of the domain and the dimension of the codomain must be also the same, right, because after all when you translate this to Fn, yeah, they are basically you are talking about a mapping from Fn to Fn. That is what a matrix is, that is what a square matrix is. So, only when a matrix is a square matrix can you have both injection and surjection. Yeah. Think of all these points that I have laid out for you, yeah, and once you look at, and the key to sort of seeing all of this is once you understand surjection and injection in terms of these important subspaces, and then think about the Rank-Nullity Theorem, which we have taken some trouble to prove. Yeah, I hope you can forgive me for the mess up I did with the initial part of the proof of this Rank-Nullity Theorem. Nonetheless, and now you try to understand what this surjection, injection and bijection imply, right. That should give you some insight. Okay. So, good, I hope that at least that concept is now clarified. With this we will now move to the next topic of linear algebra in this sequence, which is basically, now that we understand what a linear map is, this idea of change of basis. And even though it might at first glance seem like something unfamiliar to you or a bit daunting the way I have put it, I assure you that any one of you who has done a preliminary course on control theory and has is familiar with state space methods and state space representations, etc., I assure you that you have already done this change of basis, though you might have not known it by the same name. It is something that we in state space parlance often call as a similarity transformation. Yeah, but what is basically a similarity transformation in terms of matrices is basically nothing but a change of basis that we say in terms of these abstract vector spaces. Okay. So, what is this idea of a change of basis? Now, suppose you have, again without exception this will always be a finite dimensional vector space, FDVS, that is the short form I shall be using. Okay. So, suppose V has a basis BV which is given by V1, V2 ... till Vn, and of course the choice of this basis is not unique. So, let me choose another basis which is B tilde of V, okay, that is given by U1, U2 ... till Un. So, these are the V's, these are the U's. So, let us say this is the old basis and this is a new basis now in terms of which I want to represent a vector. Okay. So, what do I need to understand? It turns out that in these linear subspaces, in these and in terms of these linear maps, if you want to understand a linear map, the key to understanding a linear map over finite dimensional vector spaces is to understand what a linear map does to each element in a basis set. Okay. Once you know what a linear map does to each element in a basis set, you basically know what a linear map does to any arbitrary element in the vector space. That is a very crucial and pivotal point. That is why we love linear maps, right. They are so easy to deal with. Again, getting back to the point on hand, that we are very fond of these linear maps, and even if we have to cook up many linear maps to approximate or capture a particularly complicated nonlinear map within some reasonable bounds of approximation and conservatism, we would still prefer to go about it in that fashion, right, because we understand linear maps so well. We have a complete handle over these, or so we would like to believe, right. Okay. Now, the fundamental point that I am trying to make here is, suppose we have a vector V, of course this vector V belongs to the vector space V, which is given by alpha 1 V1 plus alpha 2 V2 plus ... till alpha n Vn. Okay. So, then you can say that the representation of B, this vector V in terms of the first basis is basically an n tuple alpha 1, alpha 2 dot 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 till alpha n. Yeah. And now the question is, I wonder what the representation of this vector v in terms of the new basis, that is b tilde, is going to be like. So, given that I have information about what its representation as an n tuple in terms of the old basis is, I want to find out what should be its representation in terms of the new basis. What other information have I been given? The additional information I have been given is that every element in the new basis can be represented in terms of elements in the old basis in the following fashion. Of course, look, after all, this uk also belongs to v and bv is a basis for v. So, every element in the new basis can therefore be expressed as a linear combination of the members in the old basis, right. So, how do we write this as? We write this in the following fashion. We write this as tik v vi, I am sorry, tik vi, I going from 1 through n. That is just a short way of writing, that it is T1k V1 plus T2k V2 plus dot 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 till Tnk Vk. In other words, if I want to represent the kth element in the new basis in terms of the old basis, here is what the representation would look like: T1k, T2k dot 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 till Tnk. Okay, good. So, given that I know all of this, so I know the old basis, I know the new basis, I know the representation of each member in the new basis in terms of the old basis. These are the things that are known to me. What am I being asked to do now? Given any arbitrary vector represented as an n tuple in terms of the old basis, the question before me is, what would be the representation of that arbitrary vector in the coordinate system defined by the new basis? Yeah, and we will see that at the heart of this is again this matrix representation. How so? So, let us see. Okay. So, let us write this down now. So, now V is equal to, where was I? Yeah. So, let this be beta 1 u1 plus beta 2 u2 plus dot 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 till beta n un. You might ask, why n? Of course, two basis sets may have different elements, but the number of those two basis sets elements in the basis sets must be the same, because they uniquely define what is a unique property of the vector space, that is the dimension. So, you might choose different bases. I might have a vector space for which I choose one basis, you choose another basis. Our bases may completely be different, right. But the thing that is common to the two basis sets is that their cardinalities, the number of elements in those two basis sets must be the same. Yeah, if they weren't so, yeah, then it would violate the fact that the dimension of a vector space is unique, right. After all, the number of elements in the basis is basically what the dimension is. So, therefore, although u1 through un is maybe a completely different basis with no common element with the set from v1 through vn, the number of elements will still be n. Okay. So, that means that v represented in terms of the new basis as a coordinate is basically this beta 1, beta 2 till beta n, and the question is, I want to obtain these beta i's. Okay. So, these are unknown to me. I wonder how, by knowing these elements alphas and these elements t's, can I get this betas. Okay. So, that is the problem before me, and it turns out it is not very difficult now. You might have, as you might have already guessed. So, what do? Look, I know what these u's they look like. in terms of the v's, right. So, I just substitute it here. So, what do? I write this as beta 1 times, and what is u1? It is basically T11 V1 plus T21 V2, T11 V1 plus T21, I hope, yeah, 21 V2 plus dot 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 till T N1 Vn, yeah, plus beta 2 times T, hang on, what is going to remain common? Let me be a little careful here, the second index. So, T12 V1 plus T22 V2 plus dot 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 till T N2 Vn plus dot dot dot, last element is beta n, and now I have, hang on, let me be a little careful here, not mess this up. So, what I am basically summing over is the first variable, yeah, T1. So, it is going to be T1n V1 plus T2n V2 plus dot 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 till Tnn Vn. Yeah. And what are these? This is nothing but, after all, the same thing, no, alpha 1 V1 plus alpha 2 V2 plus dot 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 till alpha n Vn. Yeah. Yeah, I'm so far I'm doing good, I hope, right. So, we have the representation in terms of BV of the vector which are given by the alphas. We have the representation of each u in terms of the elements in BV which are given by this, right. And now we want to find out the representation of this arbitrary vector v in terms of B tilde v, right. So, now what do we have here? Well, what we have here is, if I now equate the coefficients on either side, I will have that alpha 1 minus beta 1 T11 plus beta 2 T12 plus dot 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 till. Now, if I push this all on one side of the, this is something, remember, we have already done. So, the set from V1 through Vn is linearly independent, therefore, if I push everything on one side, then each of the coefficients of V1, V2, V3 so on will be equal to 0. So, I have alpha 1 minus this till beta n T1n is equal to 0. Likewise, I can have alpha n minus beta 1 T n1, I believe, n1 Tn2 V2 plus beta 2 Tn2 V2 plus dot 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 till beta n Tnn is equal to 0, which means what? Which essentially then means that I can write this alpha 1, alpha 2 in a succinct manner as equal to, notice this very carefully now, what is each of these indicating to me? Yeah, it is indicating to me that this is T11, T12 dot 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 till T1n, and this is T21, T22 dot 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 till T2n, until the last fellow here is Tn1, Tn2 dot 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 till Tnn, times beta 1, beta 2 dot 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 till beta n. This is a very crucial relation. Okay. So, provided I know this, and I know this, yeah, I should be able to solve for this. Of course, you might say, what is the guarantee that this inverse always exists? Well, the guarantee comes from the fact that after all, what are these columns? And this is where it is going to be crucial. Look at these columns here. What is this column here? This column is basically the representation in Fn of uk, right. So, each of these columns, this column basically, if you look at it, this is basically u1 represented in terms of bv. This column is u2 represented in terms of bv, right. So, similarly this last column, this is basically un represented in terms of bv, and since all of these are linearly independent, yeah, therefore their representations must also be linearly independent after all, right. This is just a basis representation, and therefore the columns of this matrix are linearly independent, thereby ensuring that it is a full column rank because it is square matrix. It is also a full row rank. Of course, these are results, I am not really getting into the rigorous details of why column rank must be equal to row rank, but I assume that at this point you take it as a fact. It requires a proof, I must admit, but yeah, since we are not getting to that, getting drawn into that discussion, so I hope that you agree that this is going to be invertible. So, therefore, it turns out that given that I have the representation in terms of bv and I want to find the representation in terms of the b tilde v, what do I basically need to know? I basically need to know that how can I represent each element in the basis in terms of the basis which I already know. So, I have a new basis in terms of which I want to express my vector, that is these betas, yeah, and I do not know these betas. What I know is that, well, if I may now write this here, so this is basically V represented in terms of BV, this is going to be T, the matrix T, and this is this V represented in terms of B tilde, right. So, if I want to get from this B tilde to this B, then I need knowledge about this matrix T here. And how do I cook up this matrix T here? Well, every column of this T is basically telling a story. What is the story it is telling? Every column of this T is telling me how every single member in this new basis, which I am now interested in, can be represented in terms of the old basis. Yeah. So, provided I understand the old basis well enough, I can represent every element in the new basis. You give me a new basis, I will represent every element in the new basis in terms of the old basis, stack them up as columns, get my T matrix, yeah, and that T matrix when acts on my new basis, representation in terms of the new basis gives me the old, yeah. So, look, what is this? This is the new basis, so the new in terms of the old. So, this is a representation of the new in terms of the old. So, I represent every element in the new basis in terms of the basis I already know, which is the old basis, yeah, and that allows me to get from this new basis, how do I convert from the new basis to the old basis, or rather if I am interested in the old basis to the new basis, then I take the inverse of that. It is just as simple as that, yeah. You want to get from basis 1 to basis 2, find out how every element of basis 2 can be represented or encapsulated in terms of elements in basis 1, yeah, that is it, that is all there is to it, okay. So, that is basically a change of basis, and this leads to similarity transformation. We will see more pictures of this through commutative diagrams in the next lecture. Until then, take care, thank you very much.